A difference equation is basically just defining a sequence in terms of previous terms. So the way that we write this, for example, t1 would mean the first term. Sometimes they write t0 as the first term. Methods are all the same, just depends on the question. In the regular maths course, they generally say t1. In applied maths, they generally say t0. But again, it doesn't make too much difference. The question will tell you. T2 would mean the second term. Tn would mean the nth term for any number n. Tn plus 1 would mean the term after the nth term. So it's the term after that, n plus 1. And similarly, t sub n minus 1 would be the term before the nth term. You also might see in some textbooks it's written as t1 or t of n. This is like the same as a function notation. They don't use this on the leaving cert, so you don't really need to worry about it. But in case you see that in textbooks, that's what that means. It's all the same thing anyway. So in terms of defining a sequence in terms of previous terms, here's what that might look like. I'll give a very simple example. We could say that tn is equal to t sub n minus 1 plus 2. So this means that the next term in a sequence is equal to the previous term plus 2. Another completely valid way of writing this is t sub n plus 1 is equal to t sub n plus 2. These mean the exact same thing because this is the next term and this is the term before that. This is the next term, this is the term before that. To see that they're the same, you could just replace this n with an n minus 1, because remember this n could be anything, and you'll see that they're both exactly the same. Now, we're not going to be too concerned about these kinds of difference equations, and the reason for that, if I bring this t sub n minus 1 to the other side, we can see that tn minus t sub n minus 1 will be equal to 2. So the difference between any two consecutive terms is 2. It's a constant. So this is actually just an arithmetic sequence. It's arithmetic or linear, you might hear it called. And these are covered in the Leaving Cert Applied Maths course. So we're not really going to talk about them in Applied Maths. They never ask about it, even though it is in the book. So the next most natural sequence we might think about is, instead of adding 2 to the previous term, what if we multiply by 2? So let's say, what if the nth term is equal to 2 multiplied by the previous term? Now these are also in the Leaving Cert Maths course, which you might come to notice in a few minutes, but these are a lot more important to Applied Maths, so this is kind of going to be our starting point. So we need to figure out a few terms here. So let's just see, what's the first term going to be? So t1, replace n equals to 1. I'll actually do it underneath. If I let n equals 1, well then the first term, t1, will be equal to 2 times t0. So the problem is we can't figure out what t1 is because we don't know what t0 is. If we let n equals 2, we also can't do that because t2 will be twice times t1, and we don't know what that is. So we need to figure out what t0 is, except we can't do that. So usually the question will give you a starting point. They'll say, for example, t0 is equal to 1. So in a difference equation, you need two things. You need a starting point, and then you need the pattern, and that allows us to construct all the numbers in the pattern. So now we can figure out if the 0th term is equal to 1, well, the first term is twice the 0th term, so 2 times 1 gives us 2. If we wanted to find the second term, it's going to be twice the first term, so the first term is 2, as we found out up here, so we'll have 2 times 2, which is equal to 4. If we want to find the third term, n equals 3, we get that t3 is equal to 2 times t2. Again, that's just subbing into this formula, which will be 2, and then t2 is 4 times 4 equals 8. I want you to see if there's a pattern here. So we have 1, 2, 4, 8. Can you see a pattern? Well, the pattern is that these are powers of 2. We have 2, 4, 8, and this is 2 to the power of 0, which is 1. So if this one's 1, this is 2 to the power of 1, this is 2 squared. You might guess that the general term is tn is equal to 2 to the power of n. And you would be correct if you said that. And the only thing is, how do we know that this works for every number? Now, you never have to prove this in Applied Maths. I'll be making separate videos to prove these things a bit more rigorously, but in case you were curious, you could sub this into the original equation and see that it's true. I'm going to do it for this very basic example, but then you might want to try it yourself for other examples, but I won't do it because it's not necessary for the exam. So if t sub n is equal to 2 to the power of n, that means that t sub n minus 1 would be 2 to the power of n minus 1. Let's check if this is a real solution, if it's an actual solution to this equation up here. Let's make sure it actually works. So instead of t sub n, we're going to have 2 to the power of n. So is it true that 2 to the power of n is equal to 2 multiplied by, and then instead of t sub n minus 1, we're going to have 2 to the power of n minus 1. Is this true? Well, it is true, because this is 2 to the power of 1, and we add the powers, and both sides are equal, so this equation is true. So that means we know that this is indeed a correct solution of this difference equation. So this is a bit of a basic example. We want to try to generalize this now, and then I'll kind of go into more detail officially about what this is, and then we'll get onto harder examples. And this is going to be the foundation upon which we build every single thing in the chapter. So that's why we're going to kind of get very general here. So in order to generalize, I'm not going to generalize all at once because that's a bit of a big jump. I'm going to take this again, but I'm going to let the first term, t0, be equal to a. And one thing that I would encourage you to do after the video is do all of this, but instead of starting at t0, start at t1 and see what you get as the answers. and they're going to be slightly different, but it should all work out the same overall. So starting at t0 equals a, we want to find a formula for the nth term. So what's n equals 1 again? Let's look at the first term will be equal to twice t0, so that'll be equal to 2a. If we let n equals 2, well then we can say that t2 will be equal to 2 times t1, and t1 is 2a, so we'll get 4, well we'll have 2, I'll write it all out, we'll have 2 times 2a, which is 4a. If we have n equals 3, we'll have t3 will be twice t2, which will be 2 times 4a, which is equal to 8a. And again, we can see a pattern. We have a, 2a, 4a, 8a. We might guess that the nth term will be given by a times 2 to the power of n, where a is whatever the first term is. So we can say that the nth term, if we don't know what the first term is, it's going to be the first term times 2 to the power of n. And that's the formula for the nth term. You can take this, you can plug it into here, and you'll see that it does indeed work. And another thing I'm going to suggest for you to try is if we did it with, say, let's say we had t sub n plus 1 equals 2t sub n. Is this the same as this? Well, yeah, except instead of starting at n equals 1, we just start at n equals 0, and we get t sub 1 equals 2t0, and as you can see, these two things are the exact same. So just to hammer that point home, that this is the exact same as this, it's just about the relationship between the terms. So for demonstration purposes, for our final generalization, I'm going to use this version instead of this version. So I'm going to use n plus 1 and n instead of n and n minus 1. So instead of multiplying by 2 each time, I'm going to multiply by r each time, okay? And again, this is just trying to generalize things as much as possible. So you might guess that if we're multiplying by r each time, we're going to get r to the power of n, and you'll see that that is indeed the pattern we get. If you do out the same thing that I did up here, I'm not going to do that though. I'm going to jump straight to the solution. When we have this difference equation, the solution will always be t sub n is equal to a times r to the power of n. And we can prove this, again, if you sub this into here, you will see that that is indeed true, just depending on what r and a are, obviously. So let's look at an example of how we could do a question. These questions tend to be very easy, though. They only come up on ordinary level, and it's kind of just the same as leaving cert math stuff. And a little side note, you might notice this is very similar to the formula for a geometric sequence, in leaving cert maths, and that's because they're the exact same thing. We're just multiplying by something each time. So if we're multiplying by the same thing each time, that's what a geometric sequence is. The reason there's an n minus 1 in the power here is because in leaving cert maths, they start at t1 instead of t0. So if you do these examples with starting at t1 instead of t0, as I recommended you to do, you will find that this is the equation you get. But when we start at t0, we just get an n in the power, which is why starting at t0 tends to be a little bit nicer. So here's an ordinary level question from 2023. I'm going to ignore the first part, it's quite basic. Here's the difference equation we're given. I'll write it up here in case it's a bit small. M sub n plus 1 is equal to 0.92 mn, and m of 0 is equal to 2. Okay, so we have our starting condition, and then we have our relationship. Now you might say, oh, we're multiplying by this each time. Here's our starting position. So we can say that m of n is given by 2 times 0.92 to the power of n, subbing into this equation up here, and that is the correct solution. However, I don't want to be just subbing, like kind of copying numbers down. I want to get you used to the method that we use for the later questions, okay? So basically what we're going to say is we know that the answer is going to be some kind of exponential, okay? And again, this will make more sense why I'm doing it this way. I'm just kind of showing the method that we're going to use for the harder questions, so just bear with this. It's okay if it seems unnecessary or long-winded. We don't know what a or rn are. We don't know what either of them are, but we do know that this is true. So we can sub into this, and it's going to be true, because this is probably going to be a solution. Well, this is going to be a solution if you sub it into here. But anyways, let's just see what happens when we sub it in. Let's just go with it. So m of n plus 1 will be a multiplied by r to the power of n plus 1. So now we have what we think the solution is. We have the question. Let's sub what we think the solution is into the question, and let's just see what happens, okay? So we're going to get a times r to the power of n plus 1 is equal to 0.92 times, and then m of n is going to be a times r to the power of n. Now you can see we have a on both sides. We can divide both sides by a. They cancel out. We also notice both sides have an r to the power of n. We're going to have to do a bit of work on that though. So if we have r to the power of n multiplied by r to the power of 1, just splitting this up will make it easier to see what's happening, equals 0.92 times r to the power of n. So now you can see we can divide both sides by r to the power of n, and then we can see that r is equal to 0.92, which is what we guessed, but you can see that we can also prove it by subbing in, that r will be equal to 0.92. Cool. So that means that m of n is going to be equal to a times 0.92 to the power of n. Cool. So now we know what r is. We still don't know what a is, though. And let's say we didn't know that a is just always going to be the first term. How could we figure it out? Well, we used this piece of information. How about we use this piece of information? So we could say that m of 0 is equal to a times 0.92 to the power of 0. Again, that's just a fact because this is our formula that we're using. So if we plug in n equals 0, I'll write that down here on the side. When we plug in n equals 0, this is what we get. But we also know that m0 is equal to 2. Okay, so this is equal to 2. So what we have is that a times 0.92 to the power of 0 is equal to 2. This is equal to 1, because anything to the power of 0 is equal to 1. That means that a is equal to 2. So you can see that in each case, no matter what the numbers are, we're going to get this to the power of 0, and we're going to get a is equal to the first term, whatever it is. So, and that's a way that we could arrive at our solution. Okay, so we'd have m sub n will be equal to 2 times 0.92 to the power of n. Now again, that might have seemed very long-winded, but if we just didn't know anything about what the formula should be, but we know what it looks like, but we don't know what a and r are, I just showed you a way to figure it out from scratch. Then, just to kind of play around with this a little bit, we'll look at some of these questions. So what's the total mass of ice lost when n is 6 hours? Well, basically, we just have to plug in n equals 6, and we'll get that m of 6 will be equal to 2 times 0.92 to the power of 6, which should make intuitive sense. We're multiplying by 0.92 6 times. That's what our difference equation is. And when you put that into your calculator, you'll get that m is equal to 1.21 kilograms roughly. So yep, so this is how much mass is remaining. That's what the context of the question is. I know I didn't really go through it, but it's not really the point. I'm showing how to do the difference equations, but I'm going through the theory quickly. Basically, m of n is just how much mass is left. So if they said how much mass is lost, well, if we started at 2 and now we're at 1.21, it's just the difference between those two. It should be 0.79. The second question might be a bit trickier. What's the smallest value such that the block of ice has a mass of less than 1 kilo? Well, that would mean that we want m of n to be less than 1. And m of n, we can't directly solve for m of, or we want to find n, but there's no n we can solve for here. But we do know that m of n is equal to this. This is our solution for m of n. So we can actually just say that 2 times 0.92 to the power of n is smaller than 1, because that's the same as what m of n is. Then we can use logarithms to solve for n. So these are called first order homogeneous difference equations. And the reason for that, first order means that there's the next term is defined in terms of the previous term once. So we have the next term and we have one previous term. A second order difference equation would have the term defined in terms of two previous terms. And then it's homogeneous means it's made up of the same stuff. That's homo means the same, and geneous means kind of like stuff. So the reason for that is because every term in this equation is to do with the sequence. So this is a term in the sequence, this is a term in the sequence. If we added like plus 3n, this isn't a term in the sequence, so now this is no longer homogeneous because we've added in something it's not all made up of the same stuff. We have terms in the sequence and we have kind of variables as well. So we'll get into those, but that was first order homogeneous difference equations.